Okay, we're back, finally. All right, so how do you solve differential equations that... Listen up. Shh. Oh, there's a Jason. Holy cow, we're starting again.
How do you do this?
Let's see, so Kevin's here, Jason's here. Hang on. So, I'm going to solve some differential equations that you can solve normally with this new method, and then show you how it works when you can't solve normally. Either you can't variable separate or you can't integrate normally.
Should I put this on desk?
Here we go. Take a look at number one. Let y equal a Maclaurin series. See, remember Maclaurin?
Yeah.
Isn't that Maclaurin? Powers of x, right? Right. Be an infinite Maclaurin power series approximating the solution curve for the following differential equations. So y is the solution to y prime equals x plus 1. Now this is really ridiculous. Can't you just integrate that? dy dx is x plus 1. Move up the dx. Integralize, you get x squared over 2 plus x plus a constant. Figure out the constant, right? This is incredibly easy to do by variable separable. That's not the point. The point is, how does this other method work so that we can use it when we can't variable separate, okay? So, use this given Maclaurin series to solve the differential equation. Here we go. So this is number 1 on 107. And we have that y prime is x plus 1. But y is this Maclaurin series. A plus bx plus cx squared plus dx cubed plus ex to the 4th. How far does it go? F and g, plus f x to the 4th, 5th, plus g x to the 6th, plus, right? All right, so what's y prime then? So what do you get? The derivative of a, which is a constant, 0. Derivative of bx with respect to x is b. Okay, then plus 2cx plus 3dx squared plus 4ex to the 4th plus, whoops, did I mess up? The 3rd, right? So 5 fx to the 4th plus 6gx to the 5th plus. Okay. Now remember the equation we're solving. It says that y prime equals x plus 1. Okay. So, and one other thing. Not only is y prime equal to x plus 1, we have an initial condition that y of 0 is 2. All right, so right away, if I plug in 0 in the first line for all the x's, and I let y equal what? So that tells me what? All the zeros out except for a equals 2 then, right? This is the method of solution. If you can get the coefficients a, b, c, d, e, and f, you're good. You get the whole power series. That's the solution curve. Well, that'll model the solution curve, right? Okay. Now it says that y prime equals x plus 1. Okay. See, y prime equals x plus 1. Let me write it this way. All right. So what does that tell you? I got A. Do I have B? For this one here? Yeah, but we don't know what y prime is. That's if you had an initial condition for y prime is 0, right? That would be nice. We're going to need that if it says y double prime is 0. We need 2 initials. But look, y prime equals 1 plus x. So clearly b is 1. And what's c? 2c equals, what's its coefficient? 1. So c equals 1/2. Now, realize that there's no x squared term, so this is 0. There's no x cubed term, so this is 0. There's no x to the 4th term, so f is 0. Everything else is 0. So you're done. What's y? Y is a plus bx, b is 1, plus cx squared, but c is 1/2. Isn't that the same solution we just said a minute ago by simply anti-differentiating, getting a plus c and filling it in, right? This is a lot more work. Why would you do this? Because sometimes you can't do it easy. All right, that's number one. Take a look at number 3. You can do any of the evens for homework or in the other packet, 105. Any question in 105. Okay. 106 I'm skipping because I'm sticking to Calc 4 right now. 106 is technically Calc 5. I might get to that in the screencast somewhere if you're curious. All right, take a look at number 3. Number 3 says the same kind of thing. Let y equal that Lorentz series. But now we're going to solve for y prime equals 1. All right, so y equals a plus bx plus cx squared plus dx cubed plus ex to the 4th plus fx to the 5th plus gx to the 6th. Is that it? Is that what they give you? Yeah. You keep on going if you need to. Like if you're trying to get a general term, to get an interval convergence, get a pattern, whatever. That's why, again, y prime is again what? B plus 2cx plus, nobody knows, differentiate. 3dx squared plus 4ex to the 3rd plus 5fx to the 4th plus 6gx to the 5th plus infinite series, right? But now what we got is that y prime equals y. That's the differential equation we're solving. dy dx equals y. And you have the initial condition y of 0 is 1. So what if we plug in 0 for x and 1 for y? What do you get? If x is 0 and y is 1, what do you know? A is 1. Let's write that. Now, from then on, y prime equals y, right? Y prime equals y. So b is 1. This equals 1. And then 2c equals, right? The x terms have to have the same coefficients if they're equal, right? If y prime equals y. So 2c equals b, but b is 1. So c is a half. Yeah. B is 1 because because we're setting y prime equals 1. So as soon as we know that a is 1, b has to equal 1 because they match. Right? The 0 degree terms have to have the same coefficient. The first degree terms have the same coefficient, and so forth. Because we're saying they're equal. Okay. So now what do you say? How do you get d? We got c. How do you get d?
3dx squared equals 6 squared.
3d equals, you can drop the x squared. 3d equals c, but c we got is 1/2, so d is 1/6. Okay, so 4e equals d, but d we just figured out 1/6, so e is 120. Does this look familiar at all?
Either.
There you go. 1 over 1 factorial. 1 over 2 factorial. 1 over 3 factorial. 1 over 4 factorial. Does this look familiar? Really? Guess what the next one's going to be?
1 over 5 factorial.
Multiplied by 4, multiplied by 5, 120, multiplied by 6, 720. Okay, so here's your answer. So y is a plus bx plus cx squared plus dx cubed plus ex to the 4th, and you can continue the rest. And you know this thing. This is e to the x, isn't it? Isn't that a power series for e to the x?
Wait, x squared is over 6 and x cubed is over 6.
Oh, did I write something weird? It's x squared
Over 2.
over 2.
Obvious because you put y equals y.
So we know this series. As n goes from 0 to infinity, x to the n over n factorial, right? Now sometimes you can figure out the closed form solution if you get a pattern like this. But sometimes you can't get a pattern like this. Okay, that's right. There's a solution done. So there's another proof of why e to the x is its own derivative. Isn't that where we started?
Yeah.
We want a function that is its own derivative. Duh, gave it away, sorry. Okay. So that was 3, all right? 4 is similar. Try 5. The same exact step. By the way, where does Halget come into play? If you need to generate a series that you don't know, for example, let's say you don't recognize e to the x. Do you know, remember yesterday we talked about DE solve that we never used all year? Here's another nice function we never used all year. Taylor, you ever use it? You know Taylor? All right.
Taylor's series function?
Yep. F3, calculus, Taylor. See Taylor? Yeah. Isn't that nice? Now, what's terrible here is it doesn't give you the syntax. How do you get the syntax? We'll figure that out. It's catalog,
Taylor.
right? Escape route. So, where's my
Arc-line
catalog?
function too.
Catalog, right there, where it's using it. Okay, and I'm going to look for, what are we looking for? Taylor, right? T's. T's. One alpha T. There you go. All right, Taylor. All right, so expression, variable, order, point. What? So if I want the Taylor expansion for e to the x, with respect to x, with the third degree Taylor polynomial, near a, what point? Near 0 would be Maclaurin, near 1 would be Taylor, right? If we expand near 1, we get powers of x minus 1. We expand near 2, we get powers of x minus 2. We expand near 0, we get powers of x minus 0, x Maclaurin, right? So let's do that. So just in case you forgot what e to the x is, no, I can do that too. But I want e to the x. Comma x, comma, what degree Taylor polynomial or Maclaurin polynomial do you want? Give me one. 7? I'll give you 7. And if you want Maclaurin, you're expanding near 0. If you want Maclaurin, then plug in something else. And what the hell did you just do? Oh, it's plugging in an x value into e to the x, but I gotta clear my variables. That look. There you go. Does that look like what we just said? 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x equals 4 factorial. So you can do your Taylor expansions this way. But we digress. Okay, so now what do we want? We want, whoops, let's see, we did 1, we did 3, we're doing 5. All right, so how are you going to do this one? The idea is to set a series for y prime equal to a series for 1 over x, 1 plus x, right? We know the series for y. How do we get the series for y prime? We've been doing this all day already. If this is the series for y, how do we get the series for y prime? Differentiate that. We did that 100 times already. Well, twice. And then how do you get the series for this, you know? You can use the Taylor button. Or you can do the long form of Taylor expansion, right? Or isn't this geometric? A over 1 minus r. Who's A? 1 who's r? Negative x. So 1 times the common ratio of negative x. 1, then negative x, then positive x squared, then negative x cubed, and so forth. All right, so let's do it. So this is 5. Y is still nice and easy Maclaurin. And more terms if you need them if you're trying to get a pattern for a signal or something. Y prime is the same as it was last time. Wait, stop it. And 1 over 1 plus x is like you just told me. And we're solving y prime equals 1 over 1 plus x. And they give you an initial condition that y of 0 is 1. Yep. All right, so if y of 0 is 1, what do you know already?
But it's not, isn't it?
What?
Plus, it's not plus x squared over 2 and then minus x cubed over 3. It's just,
Yeah, what about it? What's wrong with
I thought there was division.
Okay. All right, so if you plug in 0 in the first line for all the x's and you plug in 1 for y, clearly a is 1, right? Now we're going to equate this series with this series, so clearly b is 1. 2c is negative 1, so c is negative a half. 3d is 1, so d is 1/3. And 4e is negative 1, so e is negative 1/4, and so forth, right? Well, okay, let's do a couple more. 5f is positive 1, so f is a fifth. And 6g is negative 1, so g is negative a sixth. All right, so let's write out the solution. So you get y is a plus bx plus cx squared plus dx cubed, and so forth. That's a 6. Why is it? Line up. Okay. And so you get some really weird, god-awful, strange creature here. It's not that strange. Haven't we seen some series where the factorials go away? Usually it's over 2 factorial, 3 factorial, right? But sometimes the coefficient in front from the derivatives cancels some of the factorials. That's an ln, isn't it? You can actually do this by variable separable. Right? If you bring up the dx, what's the antiderivative of 1 over 1 plus x? dx. ln of 1 plus x. Plus c is a constant, so it's a shift, but whatever, it's an ln. Okay, so this was variable separable. All right, fine, great. And you can probably get a general term, you can probably get an interval convergence, all that fun stuff. Okay, but this is where it goes crazy. Look at 7. Same setup, blah, 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 but now you're solving y prime equals x plus y. Is that variable separable? Remember, variable separable involves factoring. If it said y prime equals x times y, you can divide by y, leave the x, bring up the dx, right? But x plus y, can you separate the x's and the y's? You can't. Can you? By cross multiplying or something like we usually do, you can't. So you're stuck. You can't solve this in any kind of normal way. Now, the way we dealt with this in class was, oh, let's do a slope field. At least we can get a feel for what the solution curves look on the slope field, right? Look like. But can we get a more precise analytic solution? It's not a closed form analytic antiderivative that we're going to get with the anti-differentiated differential equation, right? That was a no. Right? Why? Because it's an infinite series, right? You can't really write it down. But, and you may not even get a general term, right? You can't get an interval convergence sometimes. It's crazy. But let's see if we can get a more analytic result. Set. All right, so y prime is x plus y, and the initial condition is whatever it is. So you can get a particular solution. And y is, again, a plus bx plus cx squared plus gx cubed plus dx to the fourth plus fx to the fifth plus gx to the sixth, blah, blah, blah. All right, so I need y prime set equal to x plus y. So I got y, I have a series for y. X is not a series, x is just one term. So I got that. I need the series for y prime. All right, y prime is b plus 2cx plus 3dx squared plus 4dx cubed plus 5fx to the fourth plus 6gx to the fifth. All right, so what are we setting equal to what?
I had you in the beginning of the year, but now I
Yeah, what number you got? Oh, 0137.
Yes.
I already got your book. You got mixed up with Jake Sable's
Jake, yeah.
book. Yeah, okay. You tell him that his book card is destroyed. Do you see him at all? Okay.
Yeah.
Yeah, because he went completely nuts yesterday. He gave me your book.
I didn't make one.
So why don't you wear one?
I didn't make one.
Why not?
0137. That's
Okay.
You know what?
Lack of
Do you
support.
see him?
Lack of support.
Yeah.
Give it to him.
Okay, thank you.
Mine doesn't fit me.
Yeah, this was a... Sorry, YouTube. This was a big controversy. We just figured out.
I don't remember the number.
No. It's too small, man.
Alrighty.
I press will. Yeah, that's 50 days right there. Oh, so I see we get the tab on my check. It's gonna be a deal there.
Wait, hang on. No, we can't use that. Wait, don't tell me. And all these latecomers. Oh. All right, let's see. Do we have Saki? No. Do we have Alex? Yes. Do we have Wesley? Yes. Do we have Travis? Yes. Let's fix that. Five, six, that's good. Alrighty.
You said even.
And one on seven. Yeah, hold on. And, either that or this one question.
So let's see.
105 topics.
Wesley.
I said okay.
All right, so let's continue. All right, so what are you going to do? Well, y prime has to equal x plus 1.
I'll tell you.
Can you write a series for x plus 1?
Yeah.
What's the difference between a series for x plus y and y itself?
Plus X.
We're just adding an x here. So it's x plus bx. All right, so I'm going to write a plus b plus 1x. Is that okay? Right? Just add x. Is that okay?
Why not?
Plus cx squared plus bx cubed plus bx to the fourth plus fx to the fifth. Right? So I'm just adding 1 to the x term. Because I want a series for this equal to a series for this. I got a series for y prime, I got a series for x plus y, I just add a little x here, right? Alright, so what does this do for you?
Mr. G.
A equals 1. A equals 1. Alright. And so we got A. So what does this do for you? Great. If A equals B and A equals 1, you know what? On the right. I got A right, on the right. But I don't know on the left. So B I don't know, A I do know, and it's 1. So A and B are both 1. Okay? Yeah.
How did you get that A's to work?
Again, just like the other 3 examples, when you plug in 0 for x in the first line, everything drops out. 1 for y.
Okay.
A's got to be 1. All right, so now what do you know? You know that 2c equals
B plus 1.
b plus 1. 2c equals b plus 1. But b is
1.
1. So 2c equals 1 plus 1 is 2. C's got to be
1.
1. Okay. Now you got that 3d equals c, but c is 1, so d is 1/3. Okay. Now what? 4e equals d, but that's 1/3. So you get e is 1/12. That's a 3. Okay. And then you got 5f equals e, but e is a 12th. So f is a 60th. Is that okay so far? All right.
So guys,
Yeah.
why are we able to like?
Why we what?
Because before you were comparing y and y prime. Like, so
Right,
how-
but it's
how
saying
can we
compare
also-
y prime to x plus y. That's what it's saying. I need a series for y to get a series for x plus y. I always start with this. I need a series for y to get a series for y prime. I need a series for y to get a series for x plus y. The series for x plus y is the same as y, except it's just 1 more x.
You did that for all of them?
That's basically the pattern for all of them. The difference being here that you can't solve this by variable separable. So this is the only analytic solution you can do.
Yeah.
What did I write? I did. Plus 1 right there.
Why do you do it for B but not C, D, E?
Because I'm only adding x. I'm only adding to the x term. I'm adding to y, this whole mess, just an x. right? All right, and then 6G is F, so 6G is a 60th, so G is a 1 over 360. So here's what you got. Okay, so what do you got? So Y is A plus BX plus CX squared plus DX cubed plus EX to the 4th plus XX to the 5th plus X to the 6th times your G. All right, so what's significant here? This is the first and only time you've been able to solve a non-variable separable differential equation analytically. But what's wrong with this analytic solution? What don't I like about it? It's not closed form. It's not like, oh, y equals ln of 2x or something, right? It's not a closed form analytic antiderivative like a function, right?
But it's so small, it doesn't matter.
But it doesn't matter because you can use this to estimate your values for y at any x at any accuracy you feel like. The problem is, what's the accuracy?
What are last terms?
No, because it's not alternating. Remember the thing with the leap, the last term you leave out is bigger in absolute value than your error when you truncate? That's only true for alternating series. What about a Lagrange error term? You can't do that either because you don't know the original function, so you can't do the whole Taylor series thing, f prime, f double prime, f triple prime, to get the Lagrange term, which is the last derivative you left out. Can't do that either. So the only way to use this as an estimate for your y values at any x is to just generate millions and millions of terms and just hope for the best that your error is not too big. Because there's no way to get a feel for the error. By the way, there's no way to get a feel for the interval convergence either. Because can you get a sigma out of this? Can you get a sigma out of this and do a row test? Yeah, this is hard, but this is as good as it gets. All right, so if you wanted a homework check tomorrow, any question on the packet 105?
Yes.
Or any of the odds you skipped on
Questions
here?
aren't working. Well, we did. First of all, I can't put in.
You skipped the evens. Any of the evens.
Second of all, this is projectile. What am I putting in? Just drop.
All right, I might be recording over finals week a couple of extra things if you're curious. Some of the other packets we didn't get to, sort of interesting.
Is this for us to keep, Mr. Garcia?
And yeah. By the way, we came in 5th in the Continental Mathematics League in our region for New Jersey and New York.
That's not bad.
That's not terrible, but we've never been 5th. We've been 4th. We usually 1, 2, or 3, but I think we were 4th once, so now we're 5th
Our
once.
grade is dumb.
Yeah. Anyway, so all right, YouTube, that was fun. Have a nice.